So we have to figure out what A is, and B, and X. Okay? Because here's what's kind of cool about MATLAB. How do you solve AX equal to B in MATLAB? You do this. It's as simple as that. Right? The simplest command in MATLAB is just this backslash. And why is it simplest? Because that's what MATLAB was meant to do. Solve equations that are linear equations. That is, yes. Yeah? That's what you do with it. And that's how you do it. Backslash, boom. Okay? If you remember from linear algebra, if you had a professor who taught you that course, they maybe had you do, X equal to B by hand, up to a 3 by 3. More nasty professors would make you do hand by hand 4 by 4s. Okay, and then there's just people who want to punish you, and they make you do like 5 by 5s by hand. Okay? Now, what we're going to do is we're going to do, ultimately, things like 10,000 by 10,000. Okay? Now, you're not going to do that by hand. But it's so easy. It's even easier by hand. It's faster than doing a 2 by 2. You just go backslash, done. Out comes your answer. Okay? All right, so that's the power. So let's talk about what is A, B, and what are my unknowns. X is what I'm trying to solve for, and so I have to know what A and B are and what I'm trying to solve for. What I'm trying to solve for here is Y. Okay? So what I'm going to think about doing is setting up this problem where I'm going from A to B. And I'm going to just discretize this thing. This is my Y. And so this is, let's say, call it Y0, Y1, Y2, so forth, all the way up to, call it Y of m plus 1. By the way, what is Y0? That's my boundary. Don't I already know that? In fact, you do, right? Don't you have that Y of A is equal to alpha, in other words, on the left? And that translates to, when we discretize, Y0 is equal to alpha. Okay? And this one over here says, well, Y of B on the other end is equal to beta. These are my boundary conditions. That's just Y of m plus 1 is equal to beta. So what I'm really going to do is solve for the interior points of this thing. Right? I don't have to solve for that point or this point. I already have them. I have to solve from Y1, Y2, all the way to Y of n. So what I'm going to do is construct my vector x in this AX equal to B. The things I don't know are Y1, Y2, Y3, all the way to Y of n. Those are my points. Okay? So I know what x is. Now, what's A and what's B for this system? Well, this is what's telling me what A and B are right here. AX equal B. So the stuff that's multiplying x, which is the y over there, is all over here. So this part here is going to make up my matrix A, and this part here is going to make up my vector B. Okay, so let's talk about what A might look like. Not might look like. Let's talk about what A does look like. Be a little bit more self-assured. Big. Remember, we're no longer on the playground doing 2 by 2s. This is big boy, big girl stuff now. Okay, people get hurt. Right? So let's talk about how to build a big matrix and how you want to do this thing effectively. So first of all, this matrix, what is the structure of it? Notice, what does this equation say? When I think about a point y of t, but now it's not just y of t. These y of t's are going to be y1, y2, y3, y4. And when I think about any one of those points, what does it depend on? So for instance, if I wanted to solve this thing at y2, well, y2 would be here. It depends upon y3 and y1. It's neighbors. So you only care about your two neighbors and yourself. You do care about yourself, like -2 of yourself. If we multiply by a negative sign, it might be nicer. It'd be more positive and uplifting message. You care about yourself with +2. Okay? Because it's kind of a negative theme here. All right, so, but we'll just go with this. -2. This is how much you care about yourself. It's how you interact with yourself. So this is the diagonal of that matrix. Y of n cares about y of n like this. So when you think about this thing being here, on your diagonal you have -2 minus delta t squared, and you evaluate this thing here at Q, let's call it Q1. And then the next diagonal, -2 minus delta t squared, Q2. -2 minus delta t squared, Q3, all the way down to -2 minus delta t squared, Q of n. What are Q1, Q2, Q3? This is the value of this function Q evaluated at all the points, right? So if you look here, you have y1. At y1, you have the function P or Q evaluated there as well. So here, you'd have a value Q1 and P1, Q2, P2, Q3, P3. And you walk it all the way across to y of n over here. Okay? So these are all the interior points. And if you're y of n, this is the diagonal term. This is how you interact with yourself. Okay? Now, remember, I'm solving for this point here. Remember that this is multiplying the vector x over there, which has y1 through y of n. So y1 multiplies this guy here, which is consistent with this formula. y2, and by the way, y1 also cares about what else? Well, it cares about y2 and y0. So let's talk about y2 first of all. So the point in front. Well, here's the point in front, the point t plus delta t, the neighbor on the right. And here's the weighting of that neighbor on the right there. Okay? So here you're evaluating the next point, 1 minus delta t over 2, p of 1. Here, 1 minus delta t over 2, p of 2. It's the next off-diagonal element. Now, if I'm somewhere down here, let's think about, like, say I'm at the point y of 2. Y of 2 cares about y3 and y1. The other neighbor has a weight 1 plus delta t. Okay? So here you have 1 plus delta t over 2, p of 2. 1 plus delta t over 2, p of 3. What are the other matrix elements? 0. There's your matrix. Called tridiagonal. Tri for 3. Diagonal for diagonal. See, I'm so good at Latin. All right. It's not even Latin. I don't know what it is. All right, so there you go. Everybody go with that? Tridiagonal matrix, that's our matrix A. So your job is to construct that matrix A. Now what about the vector B? Associated with the B is the right-hand side of this. The B is right here. Delta t squared r of t. So this is pretty easy, actually. The B vector is easy to construct because this is just what's on the right-hand side. So let's do it over here on this board. So the vector B is r of 1, r of 2. Oh, sorry. There's a delta t squared there. Delta t squared, r of 1, delta t squared, r of 2, all the way to delta t squared, r of n. There's A, there's B. There's one thing we've swept under the rug. Let's get to it now. Okay, is everybody comfortable with this so far? This step is really important that you kind of work through, make sure you really have this step down, because the discretization, everything relies on it. Taking these set of equations here and translating it to ax equal to b. That's your job. Remember, when we do the shooting method, when we have a system of differential equations, your first job always in that is to turn it into a system of first-order equations. Here, your job is to say, how do I translate this to ax equal to b? And construct those matrices.